Okay.
So our strategy is just reminding you that the steps that we decided to take. So we write down the EM field as EM field expansion in terms of normal modes in a box. And the box in our situation had periodic boundary conditions, so that we could just assume that they were e to the I k dot r, with the k's being discrete depending on, just governed by boundary conditions on the edges, which is periodic boundary conditions, so they're just multiples of 2 pi over L times an integer. Okay, so that is the first step. The second step was that we showed that the energy density showed that the energy density is written as a sum of harmonic oscillators one harmonic oscillator for each mode in the box. And when we add up the energy of all of them, then we will get the total energy. And now, and these two we did, and I think we had no problem with all of that. And now we have to quantize the system. And that's where we were at the end of last lecture. We had proceeded, so I'll just remind you quickly that that we stopped with this expression, that is, and I think I really like the discussion that we were having there at the end of the lecture, which is, that is, we said that, so again a reminder, the original expression for the vector potential, so let me write that down. So A of r comma t, this is the vector potential of the box, was expanded as sum over k and lambda, ak lambda t. This is the polarization vectors times e to the I k dot r over square root of v. And we showed that we need to write down two new variables, qk lambda, which of 1, which is the real part of this ak lambda, and qk lambda 2, which is the imaginary part of ak lambda. And once we did that, then we had that the summation. So, and we had to split up this sum into two parts. For kz greater than 0, we had ak lambda equals qk lambda plus I qk lambda 1 and 2, so real and imaginary parts. And for kz lesser than 0, ak lambda to be equal to a minus k lambda star of t, and that is q minus k lambda 1 minus I q minus k lambda 2. Okay, and then I think later on, as we kept moving through the analysis, we finally wrote down the Hamiltonian. The Hamiltonian ended up being just epsilon naught k lambda sigma, where now sigma denotes this index for the 1 and 2, the real and imaginary parts. And we showed that by simply summing over only the kz greater than 0 part, we could get omega Hamiltonian that looks like this. So this is all just reminding you of what we saw last time. And I like that discussion about, what happens when k is equal to 0. Well, as we can also see from this expression here, we have to worry about like what happens when we hit kz equal to 0. Then the kx and ky still has to satisfy the minus kx ky star condition. So once again, you can split that summation into the parts that are, say, kx lesser than 0, kx greater than 0, and keep doing that till you reach the point, of course, kx, ky, kz all equal to 0. And that is a sort of singular point in the summation, because at that point, none of these splittings can be done, but equivalently also that term contributes nothing to the Hamiltonian. So, as we will show in just a second, that once we quantize this now, so the qk lambda sigma, sorry, there is sigma here as well, these qk lambda sigmas, we can now write down in terms of some new operators, which are the, and then the next step was to identify that there is a canonical momentum P alpha, which is just equal to 2 epsilon naught q alpha dot. This is like a canonical momentum for this Hamiltonian, which allowed us to finally write down the Hamiltonian as a sum over alpha squared q alpha squared plus 1 over 4 epsilon naught p alpha squared. So that was what I said, that we showed that the energy density is written as a sum of a set of harmonic oscillators, and here is the harmonic oscillator Hamiltonian, and now we just quantize it by introducing the raising and lowering operators. B. And the B's themselves satisfy the standard commutation relation. And all other commutators are vanished. So at this point, we have now quantized the electromagnetic field with these new variables Q and P, right? And we want to see what relationship this Q and P have with our electric and magnetic field, E and B, that we know are the actual fields for the electromagnetic wave, right? So we would like to put these back into our vector potential A, right? Remember, there's a chain of equalities here, right? So you got AK lambda, which is related to QK lambda, and then the QK lambdas are now related to the B's. Okay, so there's a whole bunch of substitutions, back substitutions that we have to do to get back what the relationship is between the AK lambda and these new variables B, right? But it's straightforward because we have just look at this guy. This is AK lambda over here, and I set up the AK lambda is related to QK lambda, and now these QK lambda over here are related to this new variable B, which are the operators for the harmonic oscillator. So simply I just have to take everything there, go step by step, put it back, and I will get an expansion for the harmonic oscillator, for the vector potential in terms of these harmonic oscillator annihilation and creation operators. So let's just write that down. So clearly I need that summation to be in two parts. So let me just look at kz greater than 0. So for kz greater than 0, I have ak lambda equals qk lambda 1 plus I qk lambda 2. So for kz greater than 0, I have this, and I have this expression for the qk lambda. So I'm just simply going to substitute ak lambda equals right, that is by taking qk lambda 1 and plugging in b plus ib dagger. So, and then qk lambda 2, and that is giving me a contribution bk lambda qk lambda 1 is bk lambda plus I bk lambda dagger, right? That should go, oh, right, so let's just look that way. So that is bk lambda, that is qk lambda is bk lambda plus I bk lambda dagger, both with a 1 in front of them. Right? Plus bk lambda 2 plus I bk lambda 2 dagger. But there was an I in front of this guy. So there's an I here. And kz greater than 0, qk lambda 1. That part is correct. I times qk lambda 2, that gives me I times qk lambda bk lambda 1, bk lambda 2. Okay. That is correct. Plus I times bk lambda minus n. Yeah, I'm sorry, hold on a second.
Last time expression for the Q, will it be bigger than?
Oh, I think
You don't have
I see the mistake here. There is no I in front
Yeah, there's
of
no
Q
I.
alpha. Yeah, that's it. This is just for there's no I there. Oh, good. Excellent. Good. Okay, so let's work it again. So bk lambda 1 plus bk lambda 1 dagger plus I times bk lambda 2 plus I times bk lambda 2 dagger. Cool. That brings us back to what I have in my notes. So. Alright, everybody clear? Sorry for the little confusion. When I was copying down, on this time on the board, I made a mistake of adding an I here, and that I used it. Which makes sense. The harmonic oscillator we just quantize. Okay, so with that expression, and then we also have to do the same thing for kz lesser than 0, right? Which is equal to q minus k lambda 1 minus I times, so now k lambda equals, and I know this all looks complicated, we will try to simplify in just a minute. So b minus k lambda 1 plus b minus k lambda 1 dagger, that is the same as this q minus k lambda 1, right? We'll have this term here, and then we got a minus I times q minus k lambda 2, so that's going to give me so if we want to simplify this, because it looks pretty complicated, we are going to define a new operator A, which is some linear combination of the b's such that all of this just becomes a simple expression in terms of this new operator A for all k's and lambdas, not for all kz, for example, where kz can be both greater or lesser than 0. And we'll have to then recheck, because now we are again introducing another operator, we'll have to recheck that this Hamiltonian will still, because if you remember, once I introduced these two operators, this Hamiltonian here just became a sum over k lambda sigma for kz greater than 0, just became bk lambda sigma dagger plus times bk lambda sigma plus 1/2. So we saw that in the last class, that in fact once we put in this this Hamiltonian, this expression, we get a nice Hamiltonian that looks like what you would expect for a harmonic oscillator that has been quantized. And now we are postulating or claiming that we are now going to introduce yet another set of variables or operators A, in which the vector potential will look simple. We're going to have to recheck that the Hamiltonian also looks simple. So here is our new definition. We define new operators A, and maybe some of this is often short-circuited in many textbooks, by simply at the very beginning they take ak lambda and introduce some operator A. The reason we followed this procedure was because at the beginning we didn't quantize ak. We couldn't make it a complex valued number. We had to say, or if it was complex valued, then it had to follow a very restrictive relationship to make sure that the overall vector potential is real. So if you sacrifice that at the beginning, then of course it's much easier to just introduce some new operators A right at the beginning. So that's the other approach that's often taken in many textbooks. We have tried to be a little bit more careful in the treatment here, but of course the end result is kind of very intuitive if you sacrifice that little thing over there. So here's the definition. So clearly it's just a rotation into a new basis or a new operator rather. So it's going to be for kz greater than 0, I'm just going to take bk lambda 1 plus I bk lambda 2 divided by square root of 2. I'm going to call that a new operator ak lambda. And for kz lesser than 0, I'm going to take b minus k lambda 1 minus I b minus k lambda 2. And I'm going to call that the other part of this definition over here for kz lesser than 0. And you can also see that by taking now the minus sign of this k, just to see what happens when you do that, you find that a minus k lambda, if I now interchange or put b minus k lambda 1 plus I b minus k lambda 2 up here over square root of 2 kz greater than 0, and same thing over here. This is b k lambda 1 minus I b k lambda 2 divided by square root of 2 kz lesser than 0. So if you look at these two definitions, they're essentially the same definition, especially if I pull out a factor of I. So because you can just, as you can see just by like staring at it, that the two terms are just basically just, you know, if you compare for kz greater than 0, b minus k lambda plus I, b minus k lambda looks like this guy, except that this has got a minus I in front of it. But then this has got the minus I in front of this one. So it's just the same definition written in a different form. Okay. So at this point, a k lambda and a minus k lambda are essentially identical to each other. Essentially, by interchanging the k's, we get back the same, or taking the minus sign on the k's gives us back the same definition for the operator. So now let's look at a k lambda dagger. That's going to be, okay, the same thing. We can easily write it down. A k lambda 1 dagger minus I b k lambda 2 dagger. So square root of 2 dagger or 1 dagger plus I, so minus sign. I know it looks complicated, but if it's just by taking these terms, we have made this new definition, so it's just a matter of following the algebra. Okay, for greater than 0, less than 0. And similarly, we can also define a minus k lambda factor simply by taking the minus sign on these k's. So, with all of these definitions, then we can identify bk lambda 1 plus I bk lambda 2 as ak lambda, and then this part bk lambda 1 dagger plus I bk lambda 2 dagger, that is going to be A minus K lambda dagger for Kz greater than 0, right? So keep up this expression. So what I'm saying here is that, use a different marker. If I look at those definitions for AK lambda and AK lambda dagger, then these two terms together, right, combine to give me square root of 2 AK lambda, okay? And these two terms together combine to give me square root of 2 A minus K lambda dagger, okay? And similarly, I can look at what happens with this term. These two terms together give me square root of 2 AK lambda. For the domain Kz lesser than 0, that's exactly this term over here. And then these two terms together are going to go as root 2 AK lambda, or A minus K lambda, sorry, dagger. And so we see that instead of having two different definitions for the two domains, we have identified simply a single operator which has that definitions in two different domains. And now the definition of AK lambda can simply be written for all K. We have the simplified expression that AK lambda is square root h bar 2 epsilon naught omega k times AK lambda plus A minus K lambda dagger. Okay? And the full expression for the vector potential now, because that just involves putting back this AK lambda, is a summation over all K and lambda. No, we are not splitting up into domains. That complexity is sort of hidden inside this AK lambda now. And these are all now operators. And the only difference is really that we have to divide by square root of V, and because that's the mode function, times e to the I k dot up, and there is a epsilon which is the unit vector times e to the I k. Okay? So that's a nice looking expression for our vector potential. You should also check that given the commutation relations that we derived earlier for B lambdas, for the B alphas if you like, that the AK lambdas now satisfy that the same types of, that is, check that if B alpha dagger is delta alpha prime, as we had written down over there, you need to check that implies AK lambda dagger, or AK prime, is equal to delta KK prime delta lambda. Okay. So these also satisfy the same commutation relations as the harmonic oscillator, because they have, although they have that complicated form, they're just a unitary transformation of these P's. So that makes sense. Okay, so we've written down now the expression for the vector potential, and remember I told you that the Hamiltonian, which was written as k lambda sigma for kz greater than 0 in this form, dk lambda sigma dagger, dk lambda sigma plus 1/2. Now my claim is that the Hamiltonian, we postulate, and we'll have to verify, that the Hamiltonian is also having a simple form in this, with this new operator, and now this is summation over all k lambda, no restriction, of the modes. So I'm claiming that in fact AK lambdas will now make the Hamiltonian also still look like a harmonic oscillator, and further will remove the restriction on the K's. And the only way to do it is, of course, to verify by plugging in the expressions. So I will just quickly do that. So maybe leave that part over here. So this is the original Hamiltonian, right? And I have to show that this Hamiltonian is equivalent to that Hamiltonian. Okay? So to do that, once again I have to plug in the expressions for AK lambda for the two domains. So this is the sum over all K. So obviously I can split it up into two parts. That is one which is a summation over Kz greater than 0 for all K lambda times this part plus a summation Kz lesser than 0 for of the same thing, right? And then I have to substitute for AK lambdas with that expression over there for Kz greater than 0, and for AK lambda dagger I have to substitute this expression for Kz greater than 0, etc. Maybe I should just skip that because it's, although it looks complicated, it's really pretty just following through all the algebra. So I'm going to just skip that, even though I have it here, because I want to move on to what I really want to talk about, which is the so the proof is basically, as I just said, along these steps. Split the expression into some Kz greater than 0, some Kz lesser than 0. You'll find that you can rewrite this part again in terms of a K of the same Kz greater than 0 by flipping all the Kz's. You'll see that it's equivalent to this guy, and then you can show that that will be equal to that. So it's a couple of steps. I'm just going to skip. So what is our final result? Okay, that's really what I want to focus on. So our final result is that we have found that the energy in the field can be written, oh sorry, obviously H bar. Okay, this was over there, I guess. So so the energy in the field is just H bar omega K times AK lambda dagger times AK lambda. Where K labels the spatial mode, e to the I K dot R. So K labels e to the I K dot R, which is the wave function, the eigen or normal modes of the box, as we talked about with periodic boundary conditions. Lambda labels the polarization, and the AK lambda dagger satisfy this commutation relation. This is our final sort of expression. So it's a very simple looking expression, and we have also shown that in this representation, A, the vector potential, I'm just rewriting the term over there, is summation K lambda times square root H bar over 2 epsilon naught omega times V, A K lambda, A minus K lambda dagger e to the I K dot R times polarization. Now since we are summing over all k, we are not restricted in the domain anymore to kz greater than 0. We have hidden that complexity inside operators ak lambda. We can now switch the sign of k in the second term, right? So if we break this up into two terms, we can switch the sign of the k's in the second term, and so this is two terms, summation k lambda, terms that go as ak lambda, plus summation k lambda, term that go as a minus k lambda dagger, times epsilon k lambda. So by switching to k to minus k, I get a e to the minus k lambda times e to the minus I k dot r, right? And e to the minus k lambda is just the star of the polarization vector. And so the end result is that this can be written now as summation k lambda and this is sometimes also a starting point for many second quantization treatments where they just write down that the original field has two parts, a running wave going this direction, a running wave going the other direction, and they postulate that the two parts can be then represented by this, by quantizing the field, the amplitudes of the field in front of each of those terms, the running wave going forward and the running wave going backward. They call that the second quantization postulate that these are all operators instead of just complex numbers. And from this we can also find now for a free electromagnetic field, that is, which is governed only by this Hamiltonian, which is that the electromagnetic field is only, time evolution is purely governed by its own Hamiltonian, the energy density of the field, then we can immediately calculate. So remember, each of these are now in this picture, which is sort of now a Heisenberg picture, because we have made these into operators, and these operators have time dependence. So we need to calculate the time dependence of these operators, right? So we can do that from the Heisenberg picture equation, which is just what we did for a single harmonic oscillator. But now we want to carry it out for each of the terms in this Hamiltonian. Well, that's fairly easy because of the commutation relation. So that is just, we just need to calculate this commutator in the Heisenberg picture, and that's just going to give one term because there are delta, these are all delta functions or delta Kronecker deltas, I guess, whichever, if it's a discrete sum. So h bar omega k times ak lambda, this term, right? This is the only remaining term in the sum where the index is equal, and when that index is equal, then you're left with this term, which is immediately just the same as a single harmonic oscillator for which you have found this expression. So we immediately get ak lambda t equals ak lambda 0 e to the minus I. So this part is just the Schrodinger picture Hamiltonian, Schrodinger picture annihilation operator. So we can now replace in this expression the, well, I won't do that. It's pretty obvious what you have to do. You just put in this back in here. You'll get a Schrodinger picture term times e to the I k dot r minus omega t, and then in this guy, of course, you'll get a plus I omega t. So you'll just get e to the I k dot r minus omega t, and let me cheat, put that in here, I omega t. This is just Schrodinger picture, k dot r plus I. And now we can easily calculate the electric field, which is what, remember, we were getting to or trying to get to all along. And this is going to help us now to think about things like a photon wave function and so on. So I think we get some physics finally. Okay, so using all of this. So now the electric field is just obtained by taking the Coulomb gauge, this term. So when I take the derivative of this with respect to time, this is going to pull down a minus I omega, right? And this guy is going to pull down a plus I omega. So the omegas, I guess this should all be K's. Okay. Right. So the omega k's will of course just go in here. It will look like h bar omega k divided by 2 epsilon naught b, and then there is a minus I sitting in front of everything. So the final answer, hopefully you can easily see, is just going to be summation k lambda. There's an I now, and square root h bar k 2 epsilon naught. So there's a minus I omega and a plus I omega. So I pulled out the minus I. So I end up with k lambda 0. K lambda. I guess I should pull out a minus. Oh, there's a minus sign on front of this. So that took care of that. Minus sign. This minus sign is very important. C, second. You can make it go over. So this minus sign is here. Is that clear? Right? It's just taking the derivative that pulls down minus I omega, but then there's a minus sign in front over here, and then a plus sign over here, so that gives us an overall relative minus sign. And of course, we also have to find the magnetic field from del cross A. I will leave that for an exercise again, because I want to focus on the electric field. So to get rid of this minus sign, we will add the I. So there's an I here, and there's also a minus sign. So we define yet another operator, a k, which I call nu, is equal to I times a k over a k nu dagger is going to be minus I a k over, right? So with this expression, when you put these new operators and just tilde, or it's just a redefinition of the phase of the operator. In fact, actually it turns out you could have some linear combination of these operators, a and a dagger, with some phase in front of them, and that could also be used to rewrite the field with almost any phase that you like in front of it. It's like redefining what t equal to 0 is equal to. Okay, it's like saying I'm shifting t by pi over 2, or pi over 2 omega, or something like that, and then that will pull down a factor of I, so I can just do that, or I can rotate the operators, whichever way you want to think about it. With this definition, the electric field just becomes okay. So that is our important expression for the electric field, which again, as I said, in a lot of places that can be often the starting point for the second quantization. Without going through the vector potential, sometimes people just postulate that this is the second quantized form of the electric field. I want to point out one thing which is in this first factor. So there are a couple of things I want to point out. So this first factor, which is this term in front, this is an important factor, but we've encountered it before. Okay, so if you go back to the very first class, we said that we know that this is just an order of magnitude or back of the envelope sketch argument that we did. We said that the energy density U at every point in the field, I'm just going to call that half epsilon naught E squared, right? And I said if I equate that to the energy per of the photon, right? And I have to times the volume. If I do that, then I immediately get that the electric field in a single photon, E naught, is just h bar omega by 2 epsilon naught V. So in the very first class, I talked about this, that this is sort of giving us an order of magnitude for when the field of a single photon becomes important and in what frequency range and in what sort of magnitude of the electric field, which is the region in which quantum optics is going to be relevant. We talked about that, right?
There you go.
Huh? What?
The 2's down.
Oh yeah, the 2's, yeah, that's a factor. But there's another, remember that this is just an electric field, there's also a magnetic field one. So that gave us another factor of half. So it wasn't perfect, it was just an order of magnitude. But the point is that, and in fact the square root of 2 can be got rid of if we take standing wave modes, as I'll just explain in a minute. But the point is, this order of magnitude of the single photon now shows up again in front of our operators, which makes sense. It says that the electric field of a single photon times some operator that creates or destroys a single photon times some wave function for the photon, that is what the, times the normal mode, in this case is the normal modes are e to the I k dot r, that gives us sort of the electric field for the photon in this operator language. Okay. So now another notation convention that is often used. So the notation that is often used is to say that this field has a positive and a negative frequency part. Even in the case when the field does not explicitly have a free, remember this e to the minus I omega t only comes about because the Hamiltonian is that for a free electromagnetic field, right? But, and if the Hamiltonian had some other terms, say interactions with matter, interactions with other materials, blah blah blah, whatever, with other photons, hence electrons, whatever, then of course it wouldn't necessarily have the simple e to the minus I omega t dependence for the evolution of the field operator. And in fact, later on in the class, that's exactly what we're going to solve, is what happens when you do include interactions with other field modes, other atoms, and so on. But for now, it's always pretty common to refer to the part that goes with with A, you know, this is called the term that goes with e to the minus I omega t is often referred to as the positive frequency part of the electric field. So that is, so it's a little bit confusing notation, but this is the common notation in quantum optics textbooks, that E is written as having two parts, a positive frequency part, okay, and a negative frequency part. Okay? And each of these are operators, of course. Just as these are all operators, I kind of been dropping all those hats everywhere. Because AK goes as e to the minus I omega t, this is called the positive frequency part, even though this goes as e to the minus I omega t. Okay? So this E plus denotes positive frequency, but the phase is going to go as e to the minus I omega t. So it can be a little bit confusing notation, but that's the notation that is very common. And e to the minus, that is this E minus term, which is the negative frequency, as they call it, or the negative part of this summation, goes as e to the plus I omega t. Okay? Alright, so that is sort of our, and clearly I think I don't have to write it. If you want, I will, which is E plus goes as the, let me just write it down. So this. So I guess I'm going to erase this because we have accomplished our goal, which is to quantize the electromagnetic field, and now we want to discuss what that implies. So many of the arguments we made at the very beginning of the class about the frequency dependence of this amplitude, when is it that, you know, this Hamiltonian, the energy is going to be large, then if there are lots of photons in that mode, then we can go into a classical optics regime. All of those are sort of still, as you know, for intuition are still valid. But okay, so just finishing up, this E plus RT is just summation over K lambda okay. And E minus is obviously just the dagger, this adjoint of this expression. So now let's talk about another convention for quantizing the electromagnetic field. So this is our first sort of, you know, the first method, which is to quantize in terms of traveling wave modes. That's what we have done, the e to the ik dot r. But we could also have quantized in terms of standing wave modes, right? So if instead of employing periodic boundary conditions at the ends of the box, which means essentially the box repeats for all of space, if I imagine instead enclosing the box in some metal, for example, a perfect metal such that the field has to vanish at the edges of the box, right? Then there is a factor of root 2 which will arise because when you quantize the field, now you're using sines and cosines, and when you use sines and cosines, the normalization of the sines and cosines, instead of being just 1, is going to have like a factor of half in front of it. So let me just take one term in this field. Okay, so let's start with this guy, and let's now use nu. This is just one mode. Okay, I'm not quantizing all the modes, but it's the same argument. So if I take the traveling wave in one dimension, I can have two possible modes in one dimension. So if I just take a cavity which is a mirror, right? Two mirrors, along the z direction, right? And I quantize now the two modes, e to the plus ik and e to the minus ik. Okay, right? So that's the same as this guy, right? For written down for a single mode, single frequency, omega k equals nu, right? That's just a single frequency and in one dimension. Okay, the traveling wave, this is the traveling wave operator. So again, right? This is the running wave or traveling wave field operator that I have written down over here. And this will be what I call A plus K, and this is A minus K, right? In that summation. Okay. In this summation. Okay. So this is AK, this is A minus K, and I'm calling them as A1 and A2. And again, obviously, they will satisfy the standard commutation relation. So to write this in standing wave mode, we can simply define new operators, sine and cosine. And then we get E plus, we'll have a root 2 in front of it, times and now this term right, just by substitution. So this difference now is that the electric field associated with a single photon in a standing wave cavity is now root 2 times the electric field associated with a single photon in a running wave mode. Okay? And as I said, this also obeys bosonic commutation relation rules. Again, you have to verify by just simply substituting. And the Hamiltonian, the energy, is now h bar nu times AC dagger AC plus 1/2 plus AS dagger AS plus 1/2. So effectively, okay. So that will be your total Hamiltonian. So these are a more natural choice when talking about modes in a Fabry-Perot cavity versus traveling modes, which might be a choice. For example, when you don't have a cavity, or for example, you have there are some cavities like a laser ring cavity, which is a common geometry for many lasers, in which the modes have to be thought of as purely two counter-propagating modes because there is no boundary condition that enforces that they have to be zero at either end of the cavity. It's a three-mirror cavity. So why is this important? I mean, you might say, well, if it's just purely a change in the rotation of the operators, it seems like this is trivial. It doesn't make any difference to me. I cannot tell the difference between a standing wave cavity and a traveling wave cavity because they are just purely unitary rotations of each other. Right? If they're just purely a change of basis, then how can I actually tell the real difference unless there's a physical experiment that I can do that will actually tell me the difference between these two types of modes? And the answer is, in many cases, it doesn't matter. You can quantize the system in terms of either of these and you will get the same answer for many of the relations. For example, if you were to take this and calculate the spontaneous emission rate, for example, okay? And if you started with a free electromagnetic field, except for some large box that surrounds the atom, you can calculate spontaneous emission in either running waves or standing waves and you'll get the same answer. Similarly for photoionization, remember we calculated photoionization. Same answer will arise for some of those problems. But there are a few situations where the difference between these two modes will show up. Especially when you come to small photon numbers and things like that, where, let's take a simple example. You have two running wave modes and you have an atom sitting there, okay? Versus a standing wave mode where now the pattern of the field, of course, looks stationary with in the time. But also the important question you can ask yourself is, can I tell if I absorb a photon from the standing wave mode versus absorbing a photon from the one of the two running wave modes, and just a single photon, this is what I mean by low photon number, is there a difference between those two cases, quantum mechanics? What do you think? If I have an atom sitting in a superposition of two counter-propagating modes, but I don't put any boundary condition on the ends, so these are just two infinite traveling waves, and I put an atom there, and let's make it that it's sitting at a maximum, let's say, of the interference between the waves. When I absorb a photon, what would be the difference between either the running wave case or the standing wave case? From here there are no differences, but now I'm giving you a situation where it's a hint that there will be a difference. What does quantum mechanics tell us about the absorption of this photon when the atom is sitting in these two modes, in these two situations? Sorry. What will happen to the atom when it absorbs the photon from a mode going this way versus this way? Is there a difference? The recoil. Right. We haven't taken that into consideration because in our approximation, the atom is completely stationary, right? When we started out thinking about atom field interactions. What about the standing wave case? What will happen there? So there's a recoil, as you said, right, for the running wave case. And in principle, I can tell, based on the direction of the recoil, which mode I absorbed from. Correct? I can tell that if the atom went this way, that means I must have absorbed from this direction, the other direction, blah blah, right? What about the standing wave mode? Can I tell? Does it have a momentum? Where is this momentum going? Somewhere the momentum must be going. Right? When I absorb a photon from the standing wave mode, what's happening to the momentum? It's tricky. Let's think about it. Okay?
Wait, so the two scenario is that one you have a cavity,
Yeah.
and
like
the
this
other one is you have a pair
of two modes. Yeah.
of two modes, but from the same source.
Well, we don't know, right? It's an infinitely far away, so far away that we can't know anything about it, but they're just two traveling modes that are coming in. So that's all we know about the system,
Okay.
right?
So the difference between the two is how big
The cavity is in some sense, or
Okay.
we could just say that these are modes established at the edges of the universe and they're just coming in
Okay.
to hit our atom. Yeah. Right. In this case, maybe laser beams and other.
So are we
Yeah.
okay? So are we comparing the size of the cavity in some sense to the kind of absorption
Well,
time?
I guess in some sense we're saying that the way we set up the cavity matters to the absorption or to the effect of the force on the atom.
Okay.
Yeah, exactly. Right. The idea is that the mirrors are somehow affecting the, even though these modes, they could be in principle far away, right? The boundary conditions, as we said. The fact that there are boundary conditions to some extent affects how the absorption of the momentum is going to take place from in the atom. So in the standing wave case then, right, I mean, the mirrors must be somehow altering the momentum transfer between the photon and the atom. Okay? So it's a tricky situation to think about in that sense. Another way to think about it, which has been analyzed in the literature, is that by having the cavity, the mirrors nearby and the atom in the center, you can think about there are image atoms in the system. That is, each atom has an image, which is its reflection in the different mirrors, and there's of course an infinite set of these sort of, because you can then take the reflection of this atom in that mirror, so on. And now you could think about some kind of traveling wave approximation, but now you have to think about a line of such atoms, an infinite line of atoms which is interacting with the modes, and now you can conserve again momentum as a sum over all of these sort of atoms, the real atom plus the imaginary atom. But yes, so now you can tell the difference. So there's an interference phenomenon that takes place between absorption of a photon and the momentum kick that is imparted to the atom in the standing wave case. So in fact, when we look at the diffraction pattern, so if you send in a beam of atoms into a cavity, okay, and you look at the diffraction of the atoms due to the electromagnetic mode versus having two counter-propagating waves and looking at the diffraction pattern of the atom, in that situation, there is a difference between the two because there can be interference in the standing wave cavity case. We cannot tell from which of the two modes, plus k or minus k, that the atom absorbed the photon, because the atom is somehow confined not to recoil by the effects of the standing wave mirrors, the mirrors in the cavity. So this is just one interesting phenomenon, or a difference between standing wave modes and traveling wave modes. It's pretty subtle. As I said, you have to analyze it in several different ways to be convinced of the effect. And there are some subtleties in that. And there's a discussion and further references I can give you if you are interested. So let me just see how much time we have. We have 5 minutes. So let me start by discussing now another important question that we have skimmed over. So the important idea here that I want you to take away, always remember, is sort of this expression here. That the electric field amplitude associated with a single photon is this quantity, which I have also given you how easy it is to remember by just simply taking the energy density and equating that to the energy of a photon. That is really the amplitude of a single photon, right? The electric field amplitude of a single photon, and then of course the rest of this is just a quantum mechanical way of saying that we are quantizing the electric field. Okay, so if we have done all this, now we can ask that interesting question: what is the wave function of a photon? How do I define the wave function of a photon? And this is actually a problem or a question that has a very long history. So, for example, as in Kramer and Bohm, when they were discussing quantum mechanics and how to extend it, for example, Kramer pointed out the fundamental problem with quantization or with making the Maxwell wave equation into a wave equation for a light, for photons, right? So just like a Schrodinger equation governs the propagation of the matter wave, right? That's how we learn about quantum mechanics, that there's a matter wave associated with every particle, and that matter wave obeys the Schrodinger equation, and the interpretation of the Schrodinger wave function is that the probability of finding the particle at some point in space is given by psi squared. So similarly, we can think, well, can we argue that there is a probability to find the photon in some point x, which is given by modulo E squared, and the wave equation that governs E, the electric field, is then the Maxwell equation, Maxwell wave equation. Is that the actual wave equation that governs the time evolution or the dynamics of the photon? And the one issue that Kramer's was pointing out is that the eigenfunctions or the solutions of Maxwell equation, right, go as both e to the plus I nu t and e to the minus I nu t, which means that they cannot be eigenstates of this time evolution operator in the Schrodinger equation, I d over dt. Okay? So they cannot be eigenfunctions of this operator, because the eigenfunction of this operator always has to have only e to the plus I nu t or minus I nu t, depending on the phase that you choose. That was the first issue that Kramers raised back in the 1920s when they were discussing how to quantize the photon. Similarly, Bohm pointed out, let me just finish with this one point that Bohm made, which as I was just saying, why can't we treat modulo e squared plus, okay, add in modulo b squared, right? And we want to treat this as a probability to find the photon in a point in space. Of course, these guys have dimensions of, if you multiply them by epsilon naught and epsilon naught c squared, these guys have dimensions of energy, right? So we want to divide by something, so the obvious candidate is to just divide by h bar nu and say that this is my probability to find the particle in some point x, in some region x, dx around x. So in some neighborhood x and x plus dx, this will be my probability to find the particle at that point x. And the problem with this is that as dx becomes smaller and smaller, the frequency of the photon becomes less and less well defined, because as we know, we would have to make an infinite superposition of different frequencies, so there will be no well defined nu of x. What to do about that when you make dx smaller and smaller? So these are the problems that people ran into when they were trying to quantize the wave equations for electromagnetic wave. And it was Dirac who showed how you can do this in the second quantization language, which we will now get to in the next class, but which we've already done for the electromagnetic field, but I want to show you now the connection to the standard second quantization that you might have read earlier. Okay, so I'll do that in the next class and discuss what is the wave function for the photon. Any questions? Sorry. Fast. Okay, you can always talk.